Good morning, everybody. I'm Mary Beth Tarzian. I am the Assistant Dean for Alumni Affairs and Development at the College of Human Ecology, and I welcome you here today for this panel discussion on Alzheimer's disease, new discoveries on origins and care. Before we begin, I'd like to thank you all for rising early and coming out in the rain. I know you were all out celebrating the Far Above campaign for Cornell last night. It was a spectacular event, and I'm glad you all did make it. I considered wearing my little blinky light seal, but I thought it would be a little distracting, so I left it home with my son. As you know, my colleagues will be discussing Alzheimer's disease with you today, and we are very excited to have with us Paul Eshelman, who is a professor in the Department of Environmental Design and Analysis in the College of Human Ecology. He's right here. He's sitting with two of his spectacular students, Tiffany Peterson, class of '08, and Bridget Sweeney, who's class of '06, and she's also getting her master's degree in '07. Dr. Gunnar Goris, who's associate professor of neurology and neuroscience and associate attending neurologist with the Weill-Cornell Medical College. And Professor Watt Webb, who's professor of applied physics and the Samuel B. Eckert Professor in Engineering. We've provided you with two handouts, which it seems like most of you already have. One's a fact sheet on Alzheimer's disease provided by the Alzheimer's Association, and the other is short biographies of each presenter. If you did not get a handout, can you just raise your hand and let us know, and we'll make sure you get one. Professor Webb, you don't need one. We ask that you hold your questions until the question and answer period, which is obviously at the end after our speakers have spoken. We thought we would take a poll. How many of you know somebody, a colleague, a loved one, a friend who has Alzheimer's disease? This is exactly what I predicted, that almost everybody would raise their hand. It's no surprise to us as we consider that more than 4.5 million people are afflicted with Alzheimer's disease in the United States. And with the estimation that this number will quadruple by 2050, it is more than likely that an even greater number of us will be touched by this disease in the coming years. Alzheimer's disease is the most common cause of dementia, which is the loss of intellectual and social capabilities severe enough to interfere with daily functioning. It robs active, vibrant, intelligent people of their memories over the course of 3, 5, 10, even 20 years. I too know this disease well, as my mother, who spent 67 years of her life contributing to society, raising her family, and bringing laughter to many, has carried this burden since 1996. Sorry. Although she's still the life of any party, she's quite something. She can't dress herself, and although she remembers every word to every song that has been written in the 1940s, she can't remember what she just saw on TV, and she can't remember what she read. My mother was self-confident and carefree, and these days she suffers from anxiety and paranoia. And most upsetting of all, she doesn't understand what's happening to her. She, like many people, will not recover from this disease because as of today, there is no known cure. It is with hope, however, that we turn to the research that is occurring today at places such as Cornell University, where we may gain a better understanding of Alzheimer's, its origins, how to treat it, and how to live with this disease. Perhaps it is no surprise that when we combine the best in medicine with the best in research and the most creative minds with the most talented students, the results are groundbreaking. Today we are fortunate to have the opportunity to learn about two very unique collaborative efforts. First, we will hear about a new study involving undergraduate and graduate students. This study aims to better understand how disease-driven changes in sensory perception influences the design of Alzheimer's care facilities. And second, we will learn how the discoveries of an engineer and a physician have not only revealed new possible causes of Alzheimer's disease, but how they have uncovered it, shedding light upon how to prevent the disease in its earliest stages. I read the campaign press release on Thursday. I've been reading everything about the campaign in the past few days, as have most of us. And I found a quote that I thought was befitting of this session. It was made by Dr. Antonio Gatto, Jr., the Stephen and Suzanne Weiss Dean of Weill-Cornell Medical College. You saw him last night, and Provost of Medical Affairs of the university. By bridging the distance between Ithaca and Manhattan and bringing our best research minds together to develop solutions for the most daunting health issues of our time, I am confident we will unlock scientific and medical discoveries that can improve lives around the globe. So without further ado, I'm going to turn the presentation over to our panelists. Thanks again for coming.
Hey, it's on. Good morning. Bridget and Tiffany and I are going to talk about a research project entitled Design in Support of Personally Meaningful Stimulation in Alzheimer's Care. My colleague Frank Becker is co-principal investigator in this research. As Mary Beth mentioned, as Mary Beth mentioned, Alzheimer's touches many of our lives in a very deep and motivating way. For me, it was when my mother was diagnosed with Alzheimer's and moved from the independent living unit in a continuing care community in which she was living with my dad into skilled nursing. I was in disbelief that this was actually happening. This was a loving mother and a very well-read individual, an elementary school teacher who didn't miss a beat. And I was in total denial that this was happening to her. And I was particularly pained by her cries to go home. I was motivated to do anything I could do, which was very limited. I'm a designer. I designed furniture and interiors, and so my offering to her was very limited, but I did what I could do. And so what I did was I began with a dish cabinet that an uncle of hers had built for her when she was a little girl, and that she remembered. And at the risk of insulting her by bringing this childish toy into her room, I thought, what the heck, she recognizes it. Maybe I'll bring it in and put it there for her. So I designed and built a stand onto which I mounted the dish cabinet and put some additional features, like she had osteoporosis. I was concerned about falls. I thought, well, I'll put handles on it so that if she comes up to this, there's a securing point for her. I also did the handles for metaphoric reasons, to hold her hand when neither my brother or I could be there. I had observed a behavior that was disturbing to me to watch. It was a frenetic rummaging behavior, but I concluded, well, I guess that's my problem. This is an expenditure of energy for her that probably is a good thing. So I like the dish cabinet not only for its familiarity to her, but for the limited number of rummaging options it presented to her. I also designed in a rummaging drawer. I worked more with the idea of the stand and refined it as around the notion of an anchoring element in a room that could mark place, could be above it, could be a significant picture or piece of artwork, something familiar to the individual. And I included, there are changes that happen in the brain, like deterioration in ability to sense depth. And that really is a learned phenomenon. As you're in infancy, you learn to comprehend what your eyes are seeing in terms of depth, and you can lose that apparently as this disease progresses. So doing things like trying to accentuate edges, differentiating material at edges so that the individual can better discern the difference between floor plane and table plane. So there were other ideas woven into this. And then I played with the idea of rummaging again with an insert that in the upper position or orientation, it's a rummaging drawer, an ever-open drawer. That was one of the problems on my mother's cabinet, was she would open a drawer and it would stay open and then create a risk of the piece of furniture being tipped over. Or it could be taken out and inverted and become a mantle onto which markers of or reminders of milestones could be displayed. And then I was talking with a colleague at the University of Wisconsin, Gerald Weissman. He's an architect and educator, and he's done a lot of work in the area of design for dementia. And I happened to be mentioning this piece of furniture that I was working on and mentioned the notion of mantle, and he said, well, pick up on that. The idea of mantle, of hearth, is it's an element, central element historically in the design of residences. And so to pick up on that very familiar type of element might be an appropriate thing to do. So this was an investigation of trying to represent hearth and mantle in a way that doesn't really bring fire into the resident room. But it acts as a frame to help accentuate and draw attention to a focal piece. And the mantle could be a surface for elements that could be manipulated, familiar things that perhaps are even extensions of the idea of the main photograph or the main image. So at this point also, Frank Becker and I were talking, and he pointed to a reference that proved to be very helpful to me. It took this investigation into personalization to a new level for me. And the point was, initially, sensory stimulation can provide therapeutic benefit, reduce anxiety, encourage positive behaviors, slow cognitive decline. But the key here was sensory stimulation that is emotionally laden, personally meaningful, is more likely to be therapeutic. And so Frank and I then agreed to collaborate on an investigation that carried the inquiry that I was going through to a new level, a more systematic level. And we agreed to employ design for presenting personally meaningful stimulation in a manner that acknowledges decline caused by Alzheimer's, again, decline in cognitive processing of stimulation. So what we were particularly focusing on in this, or what we are focusing on, is as sensory and sensory ability or ability to process sensory stimulation declines with Alzheimer's, how can the presentation of stimuli be done in a way that mitigates or acknowledges the decline? And so the research project that we're engaged in involves 3 stages: design, implementation, and testing. And right now we're in the design phase of this. We have done some thinking and work on what the testing should be. So Tiffany will explain this area, the design area, and Bridget's going to talk a little bit about the testing area.
So what we're focusing on is evidence-based design, and I figured I'd give you a little information about evidence-based design and what it actually is. According to Kirk Hamilton, a healthcare facilities designer, Evidence-based design is a concept that can be used to create therapeutic environments for patient care that are supportive of family involvement, are efficient for staff, and restorative for workers under stress. Evidence-based designers and informed clients make decisions based on the best available information and research studies and the evaluation of completed projects. Evidence-based design allows designers to create informed designs that can later be tested, and with this research, we are creating the evidence from which designers will design. We've come up with the term personally meaningful stimuli. It's an umbrella term that has been identified to be used in conjunction with the term personalization. However important, it serves only as an umbrella term because people, places, and objects may all potentially serve as sources of personally meaningful stimulation, depending on the individual with Alzheimer's. So within the context of this research, this term remains too broad and must be narrowed. Therefore, we came up with the term personally meaningful items. These items have been assigned, such as like individual photos, memorabilia, trophies, medals, anything that kind of has a connection to a past lifetime. And these are things that we hope to display within resident rooms that might provide a therapeutic benefit. So personalization for people with Alzheimer's does not always have the result in the intended impact. This problem spawns from a misfit between how stimuli are presented and how they are perceived, given the Alzheimer's disease-driven erosion. So an improved fit between stimuli and residents' deteriorating perceptual abilities will require that the resident room be designed to isolate and give emphasis to each source of stimulation. In this case, the personally meaningful items. It falls then to designers of the resident rooms within dementia care facilities to make personalization perceivable and thus effective in providing that therapeutic benefit we're looking for. And there's little information that actually directs these designers at the moment. And research also, there's little information about how to actually test these designs. So therefore, the following list of concepts has been developed to organize three essential categories and organize into three essential categories. So the design intervention, what we're going to be using to display these personally meaningful items like the mantle, whatever it becomes, must attract attention of the people with Alzheimer's, must hold their attention, and it must engage the person with Alzheimer's. So people who are aging generally experience changes in vision because of changes within the eye. The pupils do not react to light levels quickly. The lens becomes more opaque, which scatters the entering light, and common eye diseases such as glaucoma, diabetic retinopathy, and cataracts often arise. So in addition to aging eye problems, people with Alzheimer's experience visual problems due to the illness. Spatial perplexity, distorted depth perception, misrepresented color perception, and a reduction in the ability to perceive contrast also results. So this combination decreases the likelihood that even though a special object has been placed within the room, the person with Alzheimer's will even see it. Personally meaningful items must therefore be made visually apparent and perceivable. And to do this, designers must provide adequate contrast between the personally meaningful items and their backgrounds, and also highlight these personally meaningful items with uplighting or downlighting. People with Alzheimer's not only have difficulty in perceiving objects, but also find it challenging to maintain attention on one task, object, or story. The time needed to process a source of stimulation is lengthened with Alzheimer's disease. Therefore, competition between personally meaningful items and other potential distractions can be reduced or eliminated by finding a balance between over and under stimulation and by displaying the personally meaningful items in context. I'd like to add a note that over and under stimulation varies from person to person. In any one particular situation, one person may feel overstimulated in a space and the other might feel understimulated. Personally meaningful items may not have the positive effect on the person with Alzheimer's if they have not been explored and have not been engaged with. The ideal design intervention with personally meaningful items motivates individual activity as well as social activity and encourages tactile sensory stimulation. So I'm now going to pass the presentation over to Bridget, who will discuss assessment challenges of a design like this.
Good design, socially relevant design, results from a process that begins with evidence. Once the design has been created, the process does not stop. It goes one step further and involves testing of the design relative to the evidence-based premises upon which it was based. With the range of design decisions that can be made and the limited resources available for creating long-term care facilities and skilled nursing facilities, it is necessary that designs be tested in order to demonstrate that they can be therapeutically beneficial, improve care, and be cost-effective. However, testing is not an easy process. The fundamental challenges to rigorously testing an environmental intervention of this kind stems from the degenerative nature of Alzheimer's disease and the inherent complexity of the built environment. The symptoms of Alzheimer's disease are extremely varied and highly individual. This presents many challenges. First, level of mobility and other pre-existing physical impairments limit the general applicability of an intervention and also make it difficult to obtain a representative and large enough sample size. Second, obtaining reliable and valid results is hindered by the fact that as cognitive function and self-awareness decline, it is increasingly difficult to directly query a person with dementia on subjective states. They may not be able to accurately comprehend questions or report on subjective states of being. This means a proxy or third party must report for them. In addition, interventions that are appropriate for people in the early or mild stages of dementia may not be appropriate for people in the later stages of dementia. Finding an outcome measure that is sensitive enough to detect small changes over time is also difficult. Secondly, the built environment is naturally complex, and each person's experience of it is very unique. It is nearly impossible to evaluate the intended effect of each design feature. Also, environmental interventions can have direct and indirect outcomes. For example, a 2003 University of San Diego study found that residents in facilities where exits were well camouflaged and had silent electronic locks rather than alarms tried to exit less, but they also tended to be less depressed. The direct behavioral outcome in this study was a reduction in exiting, which leads to less restraint use by staff. The indirect outcome was residents feeling less depressed. This is because they were able to have more positive interactions with staff, which boosted their self-esteem and created a more supportive environment. It is necessary for researchers to measure both direct and indirect outcomes of an environmental intervention. This means a multi-method approach to testing must be done. A multi-method approach involves collecting data from many different sources. It involves training researchers and putting them in the environment to do direct observations. Researchers can observe subtle nuances of human-environment interactions that direct querying might not reveal. Archival data, such as health history records, or incident reports, such as number of falls per month, number of times used restraints, incidences of wandering, can also give a more complete story. Subjective and objective questioning is also critical. For example, in the 2003 study, to determine the relationship between the camouflaged exits and depression, the University of San Diego researchers utilized several measures related to behavioral health and then controlled for cognitive status, need for assistance with activities of daily living, prescription drug use, and the amount of Alzheimer's staff training. In our study, the outcomes that we will be looking for are an elimination or reduction in anxiety, wandering, inappropriate behavior, depression, aggression, irritability, shame, and restlessness. We're hoping that our design intervention will enable, and we will also be testing, for sense of self, quality of life, achievements in learning, self-confidence, feelings of belonging, personal control, and social interaction. I'm now gonna...
So again, we're early on in this investigation, and we hope that, well, we're primarily working in the design area at this point, and we hope in the near future to have results that we can share with you that will be interesting. So thank you very much for your attention.
So I'm a neurologist at Weill-Cornell Medical College, and I see patients with memory loss and do basic research in trying to understand what causes this devastating disease. I greatly appreciate the work that was just presented. It's a very important part of patient care. It's actually 100 years ago that Alzheimer's first visualized what's the characteristic pathology in the brain, plaques and tangles both abnormally accumulating in the brains of patients with Alzheimer's disease. He was a physician who admitted this patient, Auguste D. She was 51 years old, had progressive cognitive decline and paranoia. He followed her in a psychiatric hospital for 5 years, and then when she died, he looked at her brain, and again 100 years ago presented this to a scientific meeting. With little interest at the time, but in the ensuing years it became, as you know, increasingly noticed and important. For those who read the New York Times this week, in the Science Times, there was a powerful example of decline that occurs with Alzheimer's. William Utermohlen was, I should say, an artist. He's still alive, but he's in a nursing home now. An American artist working in London whose style was very, very realistic. He was not an impressionistic. He really, as you can see here. In 1995, he was given a diagnosis of Alzheimer's disease, and he decided to paint himself. As you can see, a progression occurs here, a darkness here, less expression here, and then you can see as his disease progressed, deficits really in visual, spatial processing, and then really color has left, and a remarkable decline. This was in 2000. He's still alive at age 73 and resides in a nursing home. This has been a model of what is going on in an Alzheimer's disease. You have this progressive buildup, abnormal buildup of these beta amyloid plaques. Is this better? You have this progressive buildup of amyloid plaques and tangles within nerve cells. It's the amyloid that's most closely linked with disease, with the tangles now considered secondary to the buildup, but also important. This beta amyloid is a small peptide that's cleaved out of a larger protein and glues up abnormally in the brain to cause this disease. We have medications. They help a little, but there's just no cure. And it's very frustrating as a neurologist to have that. There's a lot of advance in research. We have models. We have a lot of new exciting experimental therapies. We have learned over the past few years that risk factors such as reducing cardiovascular risk factors generally associated with stroke and heart disease are important in reducing the Alzheimer's pathology and the decline, and also things like cognitive and physical activities are important, but it's critical, and that's what this short talk is mainly on, interacting with basic scientists developing new methodologies. We have focused on this beta amyloid. How is it linked with the disease? How does a protein that's normally made accumulate and cause the destruction of synapses, the interaction between nerve cells that really are critical for cognitive functioning, and if destroyed, it leads to the dementia. In a paper that was published in 2000, we had observed, using novel antibodies against beta amyloid, a remarkable or new finding that beta amyloid actually accumulates in nerve cells as the earliest manifestation of the disease. And this has been replicated by many groups, and we continued this line of work and collaborated with an outstanding electron microscopist at Weill-Cornell, Teresa Milner, and utilized electron microscopy and visualized these small vesicles within nerve cells called multivesicular bodies, where the beta amyloid, represented here by gold particles that bind to it, normally localized to these organelles, and then with Alzheimer's accumulate there abnormally. We showed that in Alzheimer's disease brain you have a dramatic upregulation of A-beta 42. And this is a process in the brain in a neuron with also the tangles in here, paired helical filaments. This was associated with a pathology within processes and synapses. And it changed our model and from what was to that the brain is mainly composed of synaptic contacts, processes of neurons. There are many between the nerve cells. These are accumulating A-beta. Subsequently, other factors, including extracellular beta, inflammatory factors, play a role in the plaque formation. So we just needed to learn about what is the biology of this A-beta. There was not so much known in brain science on these vesicles, but cell biologists knew something, and we have a world expert in endosomes and endocytosis, our chairman of biochemistry at Weill-Cornell, Fred Maxfield, and we increasingly have collaborated with him on understanding what could be going wrong. We had to develop a model system for this, and I won't go into details, but what we do is we grow nerve cells from mice that have human genes that give you Alzheimer's disease, and they mirror the disease. Alzheimer's doesn't, aspects of the disease. A mouse doesn't usually develop Alzheimer's, but with this mutation they develop the plaques, they develop the cognitive decline. And we use cells, and we have done cellular studies, again in collaboration with Dr. Maxfield, to understand how in the nerve cells, what are the earliest steps by which this beta amyloid is causing a problem in a nerve cell. We found, for example, in a paper published earlier this year, that a waste disposal system in cells is blocked and impaired compared to normal nerve cells. The Alzheimer mutant nerve cells cannot break. They have an inhibition of this important proteasome pathway. And here we extended this to try to figure that out better, again with electron microscopy, to try to figure out what is the molecular basis of this. We're moving. I don't see the one image. I'm not quite sure this didn't work, so I apologize. This is a movie of nerve cells, and it turns off here. But what we see is we see in living cells, nerve cells, movement of these multivesicular bodies, and we see that there are differences again in the Alzheimer's neurons, and we plot out the movement. We see that these vesicles don't move correctly in the Alzheimer's neurons compared to the normal neurons, and this is plotted out here, but I'll proceed. As a neurologist, therapy is what are driving motivation for the research. And there's a lot of advancement. The challenge is going from mice to people. And it takes time. It's fraught with complexities and potential side effects. The major therapeutic avenues are to block currently are to decrease beta amyloid, to block the generation of it. A fascinating strategy was to use antibodies, the immune system, to fight Alzheimer's disease. And there was actually a clinical study that was halted a few years ago, but that in looking carefully at it showed some positive, some beneficial signs, and it's continuing at many centers. There are other strategies on the horizon. I show this because we ultimately want to connect our biology with therapeutics, and in unpublished work we've been working on how do antibodies, how can they do that? It's really been a black box in the field, how an antibody that you inject into the bloodstream can go to the brain and improve mice that have these plaques and that have cognitive decline. And we've again, with the new imaging technologies, can see that you reduce the beta amyloid in nerve cell processes. This movie does show, I'm not sure why one did, but here we're just showing we can visualize living nerve cells, add antibodies, watch them, the antibody being in red, just put aside, a little bit off, adjacent to what's an APP, which contains the beta amyloid domain. And we see we can put the antibody on these cells and they internalize these antibodies with the APP. More importantly, we see that this can protect a nerve cell in a dish, just like it does the animals in vivo, and could reverse synaptic alterations. PSD95 is a marker for postsynapses that declines early in these Alzheimer's mouse models. But what I really want to highlight is an interaction that we've started, my group, Fred Maxfield, with Dr. Watt Webb, a tremendously distinguished professor here at Cornell, who many physicians are interacting with at Weill Cornell because of the technologies he's developed over the years at Cornell. And an exciting collaboration. We actually met several hours yesterday, also with Dr. Maxfield, who was up from Weill Cornell yesterday, about this project, and develop new methods to visualize beta amyloid, to be able to observe it in living neurons and in living brains. And we're making progress, and I thought in the next few slides just show you a little bit of that. Though it is a complex process, what we're doing is we've added some amino acids into this beta amyloid domain, and we can use different colors to then observe how this beta amyloid is generated. And we make different constructs. They've been developed at Weill Cornell to then use with imaging technologies that Dr. Webb has pioneered. And over the past couple of months, we've had successes with this. We've been very excited. This is a gel. It's complex but the main point here was that these constructs that we developed we were worried that putting in other amino acids would prevent beta amyloid from being formed and wouldn't be an effective system. So this was a high-risk project when Dr. Webb, Dr. Maxfield, and I first met at Weill Cornell about this, but it worked. It cleaved the beta amyloid. And this was an image that Claudia Almeida, who works with me, gave me just Thursday evening, where she has introduced this construct into cells. You can see these two cells express this construct, and we can then study with the microscopy that Dr. Webb has developed. And we have had preliminary data, evidence we can use this to follow a molecule in a living cell, follow where molecules that we target early are compared to the same molecule, A beta, just recently made, and can, in a live cell and eventually in a live brain, first of transgenic models. Watch what happens, what goes wrong. So just to acknowledge the people involved in this project, people in my laboratory, Teresa Milner, professor of neuroscience at Weill-Cornell, who's an electron microscopy expert, Dr. Maxfield and members of his group, and Dr. Webb, who you'll hear right now. Thank you.
Well, I think you can see from having heard Professor Guras's talk why I really appreciate the opportunity to collaborate with him. And we do try to bring our technologies to bear on this serious problem of humanity. And I'm going to tell you something about methods that can address some of the problems that Dr. Guras has presented. One of the things that one would like to do is to be able to detect Alzheimer's early in its progress, because, can you hear me? Am I audible in back? In back? Okay. The reason you'd like to detect it early in its onset is that there is a good bit of belief, not any evidence yet, that if you could recognize it early, some of the pharmaceuticals that are being developed, and there are about 50 of them under test now, may work much better if applied early. So you'd like to detect it early. And so therefore, the imaging that one can do with minimal invasion is worth having a look at. And that will come out as a side issue of some of the things we do. Now, the microscopy that allows us to look inside of living tissue is illustrated in this cryptic slide, and I suggest you look at the right side. What we do is we use a laser which produces a string of pulses, and if you can focus them, think of this as a flashlight beam, only it's a very high magnification focusing. And right in the focal volume, the light is very bright, and we send in low energy infrared photons which go nicely through tissue and don't excite anything there, but we focus them at a tiny point. And here's a lens, and this is a pot of fluorophore, and that little bright dot is the only place we excite the fluorescence, because what's needed when you use infrared light to light up a dye that absorbs at much higher energy, like blue light or ultraviolet light, is we combine the absorption of two photons at the same time from this very bright pulse train of laser light, and it works. And by the way, did you know that you're fluorescent? We all are, and many of our molecules are fluorescent. One that is always interesting to people is serotonin, our mood molecule, which absorbs in the ultraviolet, and it takes simultaneous absorption of 3 photons. Well, we can use this to image inside of tissue. And our first introduction to research on Alzheimer's disease was done with a collaborator at Brad Hyman at Harvard, I have to admit. And now Brad and I collaborate by arguing with each other over the telephone. But he had a student who he wanted to watch follow the growth of these plaques that Professor Guras showed you. Here are images of the plaque. This is actually imaged with an antibody against this A-beta amyloid structure, and this is what happens when you stain it with a dye. But now what he was doing was looking at one of these transgenic mice, and he had assigned a student to measure the rate of growth of these plaques. Alzheimer's disease is a 2 or 3 decade process frequently. In the mouse, it's about 2 years process. And so he was following the growth of plaque by looking through the mouse's skull. This is just a fluid that connects the lens with the skull. And he could shine through the skull. And here's the skull itself, the dura underneath it is fluorescent. And these are globs of amyloid alongside capillaries that are attached to that layer. And so here was the data that the students sent us on the growth rate of the plaques. You can see how long he'd watched these things. It would take him 2 full days or a full day, 1 full day, to record each of these points. And so he only took them every 15 days apart. We took one look at his data and said, Rich, your data is showing a 0 growth rate. And indeed, so he went back, found a few of his points that were only a few days apart, and it discovered that these plaques, which are big and objects that endure in an Alzheimer's patient for decades sometimes, are formed within 3 days. And Dr. Hyman now tells us that they've established that it's within 1 day. How long does it take in a human? We don't know. These are, again, the transgenic mice of the sort that Dr. Gouras talked about. Now, there's another piece of this problem, and that is the molecules themselves are what I would call bad actors. Most of the enzymes, the useful molecules in our body, fold into a well-defined state, which lets them do their job. Well, it turns out that this A-beta molecule does not fold properly, and it's really loose and wobbly. So we have thought about working on the looseness and wobbliness of molecules, and we've been working with a model molecule that does form these amyloid aggregates. And so we can start out with a nice molecule that doesn't fold, and then when it can make strings, because you think of a protein as just being a stretched out string, until it binds to itself and organizes itself. If it disorganizes, you end up with a tangle, which is somewhat like these plaques. And there are a whole bunch of different pathways. What's relevant? That's a good question still after many years of research. But one of the things that can happen is that it can end up forming a rather tidy so-called amyloid fibril, which is what comprises these plaques primarily. Pathway, I don't know. Now, Dr. Gouras, I think, showed you this slide, and he's looking inside of cells at very high magnification. What I've said so far applies at lower magnification. And here's an example, very recent one. We discovered that the amyloid plaques are intrinsically fluorescent, like good many of other molecules in our bodies. And here they are. And what we wanted to know was whether the neurites were damaged if they came close to one of these plaques. In other words, when the plaque formed, does it clobber the neurons around it? And we discovered by accident, the way some of the most interesting discoveries are made, I claim we work on impossible problems. So it's only by accident we solve them. But these are neurites which are excited by an entirely different nonlinear optical property. We can take red light and turn it into green light by the little filaments called microtubules that are inside all of our neurons and form the railroad tracks for transmitting molecules out to the synapses, which are usually at the end of long axons or along them. And so they turned out to be pretty good for detecting where neurites are. How long have we known we could do this in a mouse? About a month. And so here's a slightly magnified value of that. See, this is 10 microns. Here's one of these plaques, and here are some of these neurites going by them. We don't know the answer yet. Look, here's one that looks like it's coming up to one of the plaques. But what we don't know, because our resolution is only 4 microns, that far, perpendicular to the plane of the image, are they really going through the plaques? And there's a lot of other evidence that says, from other people, that these are plaques that have been stained so that they're actually a much bigger object than the intrinsically fluorescent bit. But you can see that it looks like there's some kind of interactions. But the real issue may be the molecules itself. I didn't think this one up, this guy did. The molecule we're interested in as a model molecule has nothing to do with neurodegenerative disease, but it does form an amyloid, and it was known to fluctuate. And so there's a lot of research on it. It's called apomyoglobin. myoglobin and hemoglobin you've heard of. You need them. But this is the advantage of this little molecule is that we can put a label on it. So here's the scientist hanging on to it. And what we've been doing is looking at its folding. Now, Dobson, a nuclear magnetic resonance person in England, this is what molecule. It's made up of 8 helices, and they look like corkscrews, and they're 8 alpha helices when it's properly folded. But the thing that happens to it, if you maltreat it a little bit and warm it up a bit, it forms amyloids. And this is a lower magnification microscope picture. And why? Well, so what's needed? What have I done? Oh, this is it. Hui-Min Chen and Elizabeth Rhodes, graduate student and postdoc, she's now an assistant professor at Yale, as a matter of fact, and a couple of chemists up at upstate New York Medical, who did the labeling for us, have made apomyoglobin and labeled it with a dye called Alexa 488. And it turns out these, like most proteins, if you go to low pH or if you put them in an aggressive solvent, they don't fold anymore. So we can turn on and off the folding by changing the pH. And that works nicely because we can then watch the structure unfold by another method we invented. It was, I was led into biophysics by a chemist who came to Cornell in the early days of DNA. No one knew how the double helix of DNA got separated into 2 pieces so that you could copy it and make turn on the necessary process to produce proteins to copy the sequence. Well, so what we do, here's that same focal volume again, and what we do is we measure the fluorescence of whatever is fluorescent in the focal volume as a function of time. And I can terrify you with this time-dependent equation up here. It's actually pretty simple. Diffusion happens. Well, diffusion happens if things go in and out of the focal volume. And the other thing that can happen is you can have reactions that turn on and off your fluorescent signal. That's what the little dots are, and that's these terms. And now what you do is you look at the fluctuations of the fluorescence. Well, a lazy molecule that is not reacting can wander in and out of the focal volume. It's like the drunkards walk around a light pole. It's the same theory. And so we can see what the sort of the distribution of times is, and that's the time difference, T plus tau, and we plot the fluorescence correlations versus the time scale. Look at this, it's milliseconds. And this time here where the correlations fall off is the diffusion time. That's sort of the typical time that the molecule dwells in this little volume. Now think about what Dr. Gouras told you. He showed you pictures of the aggregates moving around inside of cells, and he said he could see a difference in the normal cells and the disease cells in how they moved. We haven't looked at that yet, but that's one of the things that our collaboration is going to let us do, and do it in a very simple, efficient way, we think, with this technique. Now, if we cheated a little bit in demonstrating this in that we slowed down the diffusion by making the solvent gooey so that as a single molecule burst through that focal volume, you could see the burst of fluorescence. The longer the molecule hung around in the focal volume, the bigger the burst. So that's part of that. If it's reacting, and it's reacting faster than this diffusion time, you get a whole bunch of additional signal up here at short times. And indeed, if we look at this apomyoglobin, here's a little bit better picture of it, those 8 alpha helices. We put a dye molecule out here, and all these colored amino acids are amino acids that can quench fluorescence. And so we watch the flicker as the dye molecule bangs near them. Here's one of these correlation functions. And if we look at a denatured and unfolded state, can you see the colored lines? It's hard to see there, but that green one tells you what the diffusion only shows you in the correlation function. And all this extra stuff up here is fluctuations of the structure. Now this is one at low pH where the molecule is denatured and flapping all over the place. But the new news here is that this molecule, even when it's folded at nice high pH, here's the green line, you can barely see it, and it's still, there's extra fluctuation. And to see these, we've blown them up here down, so you're only looking at the top corner of these plots. And you can see that we're well above the diffusion point. And the idea is we're seeing fluctuations of the structure that are going from about a half a microsecond out to, oh, looks like it's about here, a couple of tenths of a millisecond. So they're fast fluctuations. Now, are these crucial to this misbehavior of the A-beta molecule? Tune in, maybe we'll know something more about it in the next couple of years, because Dr. Gouras had talked about these new dyed-stained A-betas that they have developed, and they look like very powerful tools. We've already had a look at them. They work. So we'll see what happens in the next couple of years.